Here we're going to talk about discrete random variables. And so I went ahead and wrote the definition here, so go ahead and pause and write it down. I'm going to continue reading it. A random variable, RV, which I'll start calling it RV more often. So RV means random variable. A RV is a numerical measure of the outcome of a probability experiment denoted by capital letters X, S, A, B, etc. Any capital letter you want it to be, we can use that here. So some of the first things we need to look at, we need to be able to determine if it's a discrete or a continuous random variable. Discrete random variable. We've talked about we talked about discrete and continuous before. Here, when we're dealing with discrete, we have finite number of values. And then when we talk about continuous, this is where we can have a bunch of decimals that go on forever, such as temperature, the speed of a car, etc. So it can go on infinite number of values. So just as a quick example, let's try these two out. Example 1. And I'm just going to say discrete or continuous. I'm going to abbreviate continuous here as CONT. In part A, let's say the number of A's earned in stats in this course. So what we want to do here is we want to determine if this is discrete, but we also want to give it, we want to denote it as a random variable. So here we would just say, we'll call this capital X, because we're dealing with a random variable now. So I'm calling it capital X, and that's equal to the number of A's. And then we want to be able to tell the reader what are the possible values of this X. So X can equal 0, 1, 2, and so on, all the way up until however many A's there are in the class, which is a finite set amount. Alright, so this is, I should have wrote first, discrete. Part B, let's just say the speed of a car. Alright, well, we need to label it as continuous or discrete, and this is continuous. Then we need to label this random variable. Let's call it S, since we're dealing with speed. And we'll say S is equal to the speed. Then what values can this S take on? Well, it can take on any value greater than 0. We won't restrict the top, even though there probably is a top, but here this indicates that we can't have a negative number, and we can have any type of decimal in here. So that indicates a continuous random variable. Now let's move on to the next definition. So we're going to take these random variables, and now we're going to put them into a probability distribution. And if you want to go ahead and pause and write this down, and then I will continue reading. So a probability distribution of a discrete random variable X provides possible values of the random variable and their corresponding probabilities. So let's break it down a little bit. A probability distribution of a discrete random variable X, which, like we had in the previous example, the number of A's in the class, that would be our random variable, provides possible values of that random variable and their corresponding probabilities. So if we were to take example 1 of how many people got A's in stats, then we'd say the probability of 0 is 10%, the probability of 1 is 12%, the probability of 3 is 50%, and so on. So we'd have a table to list all of that stuff. And the easiest way to do that is just to show a real quick example that we're all probably familiar with. Create a probability distribution of tossing a fair coin. All right, so again, this is just a table that, simple table here. Here we'll say X represents, it represents what the coin lands on, so it represents outcome of coin toss, which there's only two, heads or tails, and that's how I'm going to label them, as H and T. So let's get in here and draw just a simple T chart. And what I want to do is I want to say these are my possible X, these are my possible values for this random variable, heads and tails. And I could keep going if there were more, and we'll get into some more examples where you have several values of your X. And over here, this is how you label the probability of X. So these are our outcomes, and this is the probability of that outcome occurring. So if we have a fair coin, what's the probability of a heads? It's 50%, 0.50. And same thing with the tails. So here, we just created our first probability distribution. And what I want you to notice is if you add all these down, so you sum the P of X's, the probabilities of X, it equals, sum the probabilities of X equals 1. 0.5 plus 0.5 is 1. And this will be a common occurrence, and this will be one of the rules for probability distributions. And I'll get to that here in a minute, write those rules out. But next, what we want to do is look at another example. And let's call this example 3. A basketball player shoots 3 free throws okay, so and here let's say let the random variable X is what we're going to call the random variable here, represent the number of shots made. Alright, so if I give you an example, I probably won't tell you what to let the variable be called. I'll probably let you decide, and you'll also have to decide what X values that you can take on. So here X can equal, well, if I'm shooting 3 free throws, my options are to make none of them, to make 1 of them, make 2 of them, or make 3 of them. So those are my possible X values here. So I'm going to give you the table here, and we're just going to observe a few things. So we'll say here's X. We'll call this table 1 in case I need to refer back to it. X and the probability of X. So capital X, that's our random variable. Those are our possible outcomes. Excuse me. And so I'm going to just give you the probabilities here. The probability that the basketball player makes 0 out of the 3 is 1%, 0.01. The probability that the basketball player makes 1 is 10%. The probability the basketball player makes 2 is 38%. And the probability they make all 3 is 0.51. Alright, so this is another example of a probability distribution, and these will become fairly familiar to us. We'll be using them a bit. Some things to note here, just so we can get on the same page. Just say I gave you this table and I asked, what's the probability of 1? The probability of, that's saying the probability of 1, meaning the probability that the basketball player makes one free throw. So you come up here and find 1, and that's equal to 10%. And that works the same way for all of these. Probability of 3 would be 51%. All right, and also notice here, if we add all P of x's, it equals 1. So that's another thing here. Notice 0.1 plus 0.01 plus 0.1 plus 0.38 plus 0.51 is equal to 1. All right, and this leads us into the rules of probability distributions. So rules of a discrete probability distribution. And the first one is, we've talked about several times, it's the sum of all the probabilities equals 1. This is just a fancy way, a shorter way of writing this up here. This means the sum, so add all, that means the sum of the P of x's has to equal 1. All right, and then number 2, and just watch what I write here for a second. So I'm going to say I have each probability has to be between two values. Each probability has to be between 0 and 1. We can't have a negative probability, so meaning none of these in here can be 0. None of these probabilities in here can be less than 0. They can't be negative, and they can't be greater than 1. All right, and so if you were to sum all of these together and it came out greater than 1, then it violates this rule. If a single one of these probabilities is greater than 1, then that violates this rule. If one of these was less than 0, then it violates this rule here. So just some helpful info there, and we'll be using this, and it's good to know this info here. All right, next what we want to talk about is the expected value, which is the same thing, which is similar to the mean. Except here, with expected value, we're talking about what our long-term expected value is to be. So let's write this. The expected value and we can say, or mean, of a discrete random variable, RV, is denoted as capital E of x. The formula is, so anytime you see this capital E of x right here, that means we're talking about the expected value of a random variable. The expected value of x is equal to mu, the mean, times x. This is what the book writes, but we're not going to use it. That's what some books write. Some books use this. But what we're going to use is, so we start with the sum of all the x's times their probabilities. That's what we will be using. So what this is telling you is it's saying to take each x value and multiply it to its probability and then sum all those together, and that gives us our expected value. So what I want to do is I want to go back to our basketball example, and we're going to do that now. So here is example 4. Find E of x for example 3. So let's write our probability distribution again. X, P of x, our x values were 0, 1, 2, and 3. And these were, I'm just going to write them and not talk. Alright, so there are those. So now what we want to do is we want to add on another column. And this one is going to be what's inside of the parentheses right here. This x times p of x. So x times the probability of x, which are just these two multiplied together. X times p of x. So we'll get 0 times 0.01. And I'll write some of these in here. So it's 0 times 0.01, which is 0. And then it's 1 times 0.1, which is 0.1. Then it's 2 times 0.38, which is 0.76. And then 3 times 0.51, which is 1.53. And then what we do is you want to add down. Add all of these. So when you add all of these down, what you get is you get 2.39. And what we can say is E of x is equal to that. All right. So what does this mean exactly? What are we doing here? What does expected value of x equals 2.39 doing? So this doesn't mean that we're going to make 2.39 shots. So that's something to not be confused about here. What the expected value is doing is it tells us about the long-term effects of having this probability distribution. So so on any given time that we shoot 3 free throws, we're either going to make 0, 1, 2, or 3. But over the long run, as long as these probabilities stay the same, we're going to, on average, make 2.39 on every single time we go to the free throw line. So let's make that a note here. Note, E of x, the expected value, gives us the long-term results. That is, if we did this experiment an infinite or it could be really large, an infinite or really large times the expected value is the number of successes we would expect to see. Alright, and one more thing here. We're not going to get into actually how to work this right now, but it will definitely be on the exam and something that we need to know. I'll post a video of how to do this in the calculator, how to find the expected value, and how to do this next portion. So the standard deviation of a discrete random variable is, so we have sigma sub x, meaning we need this x here so that way we know it's the standard deviation of a random variable. And there's going to be, so there's two different things you may see. I'm going to write two of them here. So you might want to watch just to start. because it's kind of long. So we have the sum, then we're going to open a bracket, and so we take each of the x values and we subtract the expected value, and then we square that, and then you multiply that value times the probability of x. Notice here I used brackets around e of x. I will typically start using brackets the whole time around e of x. It just helps kind of break things up. Or instead of e of x, it's the mean of x. So it's the same formula, just going to replace it with mu of x squared times the probability of x. So just wanted to get that out there. This will be on the exam. I'll post a video about how to use a calculator with this one. That's it for now.